let's give this a go. Alright, in this class we're going to be having a look at the exponentials and logarithms side of things, focusing mainly on the exponential stuff, on both how we solve exponential equations and how we graph exponential equations. So, without further ado, let's get into it. So, exponential equations, what do I even mean by that? Well, the exponential is a special kind of function where instead of having the x just sort of in line with all the other terms, the x variable is actually raised as the power of some base, right? Like this one here that I've highlighted being 3 to the power of x, 3 being the base and x being the exponent. Because the variable is in the exponent, in the power, it makes simple rearranging like we would do via algebra challenging. We can't really solve these the same way that we can solve other equations. And so it turns out to be the case we have to have a unique way of doing things. Depending on the format of exponential equation that you have will depend on what kind of method that you use. And we're familiar with this idea of needing multiple ways of solving things from like quadratics, for instance, where you have a factorizing approach, you have a completing of the square approach, and you have the quadratic formula approach, all of which get you to the same end result. A similar sort of trio of options are available for exponential equations, starting with the simplest, which is going to be the equating exponents approach. So this is an approach that is used for these more simpler equations where you only have one exponential in the equation and everything else is just a constant, right, that can be sort of combined into one single constant. When you have it in this stage, your goal here is to try and figure out a way to rewrite any exponentials that do exist in the equation to make sure they have the same base. Now in this case we only have one, right? But the idea is if you have multiple, you'll only be able to use this approach if you can get them all down to the same base and combine them all into each other. In this case, there's only one in there and it has a base of 3. So we're sorted. What you also want to do in this case is also look at the constant term that you have as well and try to rewrite that as a new base and exponent pair. So for instance, knowing that we have a base of 3 here means that you want our constant to also have a base of 3, which in this case we could rewrite 27 as 3 to the power of 3. Now that we have a simple equation like this, 3 to the power of x is equal to 3 to the power of 3, because the left-hand side and right-hand side bases are identical, we don't really need to consider them anymore, and we just need to consider what's in the powers, right? This is saying 3 to the power of something is equal to 3 to the power of 3. By a very quick observation, we can determine that x is going to be 3. Alright, if I put the number 3 there, left-hand side is equal to right-hand side. Now that's a very simple example. We'll look at a slightly more difficult one, where we've got 2 exponentials in here. Again, first goal, try to get it down to the same base. This won't work unless you can get everything down to the same base. In this case, you got a base 25 and a base of 5. 25 can be split into the 5 squared, and then from there you can use your index laws to distribute that power through the remainder of the exponent, right? So when you have 5 to the power of 2, that is also to the power of minus x plus 2, it distributes via multiplication. From there, we can see both equations both sides of the equation have the same base, so we can now ignore the base and just focus on equating the exponents. Left-hand side exponent equals the right-hand side exponent. In this case, it's just linear. There could be God knows what goes on in here, right? That could be a whole polynomial for all we care. All we're doing is making sure that we're getting out of this whole exponential equation business and working in equations that we already know how to solve. Any questions about that approach so far? Cool. So that's used for the simpler stuff. There will be some scenarios where you won't be able to condense all of the exponentials down into a single exponential. Like this one here, right? you got 3 to the 2x plus 6 times 3 to the x minus 27. There's a lot going on there, right? There's no nice and easy way to combine everything down. We're not going to be using an equating exponents approach. We're going to be using what I refer to as the quadratic solution to this exponential equation. It's a bit more involved as to how you actually do it. Fundamentally, it just sort of boils down to substitution. We look at an equation that is more complicated than we otherwise would like it to be, and we try to figure out what is a way in which we could substitute something in here to make it look more like something else we already know how to solve. What we'll notice in this equation here is all the exponentials in the equation have the same base, or could be written to have the same base. That was a common before. That was a requirement before, and it's a requirement here as well. As we can see, already done. All these have a base of 3. All we're going to do from here is recognize that the way the powers of these are organized, they're organized in a descending order. You know, you've got 3 to the power of 2x, 3 to the power of 1x, and technically 3 to the power of 0x would be here. You've got this descending powers of x. When you have that, what you'll notice is that that's similar to how a quadratic works. You know, x squared and x and then a constant. So what we do is we take the simplest form of the exponential that we can, which in this case is going to be just the basic 3 to the power of x, and then replace that with a substitution. In this case I'm going to replace it with the letter a. When you do that, this equation now suddenly looks like something we know how to solve, and now looks like a quadratic. All we're doing is replacing every instance of 3 to the power of x with a, and because that was 3 to the power of 2x, the a is now squared because it's 2x. To see a little bit more detail as to why it becomes squared here, you can use that index law that we looked at earlier, which was if you have power to power, those powers multiply, so you can also split them off in the same way. 3 to the power of 2x is the same thing as 3 to the x squared. Now that you've got it down to exactly 3 to the power of x, it becomes much more obvious why replacing each of these with an a does in fact get you here. I'll just pause there for a bit. Is there anything that needs to be clarified about how that conversion's happened? Cool. Once you got it into quadratic form, all we're doing is solving it just like we solve any other quadratic. In this case, factorization is pretty quick and easy. We can spot the 2 factors required to add together and times together, giving us our solutions for a. But we don't want a solutions, at least not as our final answer. We were told to solve for x, right? We're trying to solve the x variable. We put a in there just to simplify things. We have these 2 solutions for a. All we're going to do is replace a with what we substituted it, 3 to the power of x. So now instead of having a equals -9 and a equals 3, we now have 3 to the power of x equals -9 and 3 to the power of x equals 3. What we'll notice is that these are quite simple exponential equations, so we go back to the first approach of just equating the exponents together. This one has no solution. There is no power of x that would work out to give -9, and this one has a fairly obvious solution, which is x equals 1. Alright, if you put a power of 1 here, you just get 3 equals 3. Any questions about that procedure? Okay. One of the questions that comes up, at least implicitly, is like, why does this have no solutions? Why is there no power of x that works out to give -9? We'll see that more so in the graph of what the function actually ends up looking like. So this is what your typical exponential ends up looking like as a graph. It has an asymptote at y equals 0. It never actually goes below this horizontal line, this x-axis, and all it does is curve up and to the right. So for a graph like this to ever equal -9, it would have to be down here. which in this case it does not go to. And you can observe just by substituting in a bunch of values what the overall shape of the graph might look like. Now I know I've got a base of 2 here, but we had a base of 3, but it's the same idea. All right, instead of just having, do I have an example of the 3s? Not quite. Instead of having 2s there, you just have 3s there. Right. Basically put, as your x value gets larger, the power, the index, is getting larger, and so the y values are going to start from roughly 0 and then move up to infinity. Whereas when you start getting into the negative region, you now have negative indexes. And negative indexes don't make the function negative, it makes the whole numbers into a fraction version of themselves. So 2 to the power of negative 1 is the same thing as saying 1 over 2. You flip it as if it were a fraction. So none of these negative numbers ever actually get you a negative result. They just get you a smaller and smaller fraction, which is why we see it just gets closer and closer to 0. It never actually flips to being negative. Hence, this will not have any solution. Okay, I kind of briefly touched on this earlier, but let's just recap it. So when we're going to be using our quadratic solution if we can identify namely these descending powers of x. Right? You've got this instance of 3 to the power of 2x, 3 to the power of 1x. Sometimes it might not be so obvious. Sometimes it tends to be a little bit hidden, like this question that we have here, right? 9 to the power of x and 3 to the power of x. Well, both of those are just power of x, so it's a bit harder to see that you might be needing a quadratic solution here until you realize that 9 can be rewritten as 3 squared. Right, 3 squared now becomes 3 to the power of 2x, and now we have those descending powers of x. So we're always looking, no matter pretty much no matter what the exponential equation is, you want to try and get all the bases the same. The other thing, again, so if you do have a question that is a bit less obvious to spot there and you forget about the idea of rewriting it, then one of the things you can do is start looking for coefficients on your exponentials. Just the general complexity of an equation like this, where it has like 3 or more terms, typically is going to lend itself to some sort of quadratic solution, especially if you have like multiplications on your exponentials, multiple exponentials in the equation, mixed with constants. You know, it's just the overall complexity of thing that can alert you to the fact you're going to be using this kind of approach. Okay, and the last approach you can use for solving exponential equations is the logarithmic solution. So this is also used for when you're trying to solve relatively simple exponential equations, like this one here, right? 5e to the x is equal to 4. The approach here requires you, well, firstly to understand what the logarithm is. So if you guys haven't covered that yet, we'll go into more detail on that in a later lecture. But for now, for those who have, all we're simply doing is starting by rearranging it to get the exponential term on its own. So rather than having 5e to the x equals 4, you now have e to the x equals 4 over 5. From there is a conversion formula. The exponential and the logarithm are very closely related to each other, as you will have already seen or will start to see if this is the first time you're looking at them. There is a way to convert this equation directly to this. I won't get into any more detail beyond that. But yes, essentially you're trying to do some sort of conversion formula to put the power of the exponential out of the power and into something where you can rearrange to get on its own. That's pretty much it so far. Any questions about the solving of exponentials? We'll get into some examples, unless anyone wants me to clarify any conceptual issues. Okay, I'll get a screen grab of this summary page so we can see the overall steps. I'll put that in the chat. Let's have a few goes. So let's see, we'll start with one that isn't super obvious. Let's go with maybe e over here, 2e. I'll start writing that up. In the meanwhile, let's have a think about how we'll do it. Okay, got 3 to the power of 3n times 9 power of minus 2n plus 1 is equal to 27. Okay, there's a little bit going on there. Our goal is to solve for n here. We're doing 2e. What are we going to do to start this one off? I'll give you guys some time to read the summary, or otherwise think of an idea. I'll give a hint, which is one of the first things we're going to care about is making sure the bases of all the exponentials, or ideally all the terms in the equation, are the same. We've currently got a base of 3 and a base of 9 for the exponentials, and we've got a constant of 27. All of these could have a common base. What is that common base? Nine turns into 3 to the power of negative 4 and plus 2. Yeah, probably. Let me quickly suss that out. So basically you're converting that 9 into 3 squared. 3 to the power of 3n times 9, which is now 3 squared, minus 2n plus 1 equals 27. And then you've also done the next step, which is try to distribute that through. So let's have a look. 3 to the power of 3n times, so 2 and 2 is going to get you to the negative 4n, 2 and 1 plus 2. So yeah, exactly right. What we've now done is convert them down to the same base, and you've also taken it a step further to also simplify things further. And another step you've mentioned, which is converting the 27 into 3 cubed. Right, 27 is in fact 3 cubed. So not only can we get the exponentials on their own, on the same base, we can also get the constant to have the same base as well. Nicely done. Cool. Okay, everything's got the same base now. We could dive right into simplifying things further right now if we wanted to, or we could take things a step further with our exponentials. What might we do from here?
You can combine the factors.
Yeah, combine the factors. So you mean maintaining the exponential form and just sort of combining these perhaps?
Yeah. So 3 to the power of 3x minus 4x plus 2.
Yep. So basically using the index laws to do the addition of those indexes. Yeah.
Yep.
3n minus 4n plus 2 equals 3 to the 3. I'll also take it a step further. So it's going to be minus n plus 2 equals 3 to the 3. Yep, that works. What else?
The left-hand side and the right-hand side have one term and they have the same base, so we can equate the exponents to each other.
Bang on. Yeah, perfect. Same base, we don't have to care about it anymore. Minus n plus 2 is equal to 3, minus n is equal to 1, n is equal to minus 1. Nice. Yeah, we can go straight at it by combining everything down until we have one on the left and one on the right, and then equating things. You could also go even a step further and identifying that because these are all multiplied together, there is already an implied plus between them. So you could even at this stage, if you wanted, well, I guess at this stage here, if you wanted to, write 3n plus minus 4n plus 2 is equal to 3. Doesn't really save you much. You're just like not writing those bases anymore, but that's literally about it. Just thought I'd mention it in case you were curious to do that, because it does save you a whole 3 characters to write. Wow. Time saving. But yeah, that's that kind of question. So that's what pretty much all of question 2 is doing. Do we want to see anything more from that question 2? I guess same thing with question 3 here. All of these, questions 1, 2, and 3, all have the same approach to them. Does anyone want to see any more of those? I think maybe the only one that might feel a bit different would be like when the fractions get involved. Are we all familiar enough with how to work with the fractions? Or do we move on to like the quadratic formula approach? Sorry, quadratic solution approach. Okay, let's move on then. Quadratic solution approach. If you change your mind and want to go back and have a look at one of those, that's fine as well. Just let me know. So let's see. Yeah, I guess any of these question 4s will do. Let's just do 4a over here. So 4 bracket 2 to the power of 2x equals 8 bracket 2 to the power of x minus 4. Okay. What are we going to do here? It's going to be a different approach. I've already given away that we'll be doing a quadratic approach for it. 8 to the power of 2x equals 16 to the power of x minus 4. Oh, okay, so the brackets don't work quite like that. When you have brackets that are raised to a power, because this term is raised to a power and this one isn't, you can't necessarily just distribute these coefficients directly in there. They would also need to be, like, there's a way to do it, but it's not something you really want to do, and it's not super neat like that. So unfortunately not quite that. One of the first things we want to do here is make sure, which is already the case, that all of the all the bases are the same, right? Which they actually are in this case. 2 to the power of x, 2 to the power of 2x. from there, if we're thinking about the quadratic solution approach, once we've got all those exponentials in that common base, if we have a look back at the screen share, the next thing to do is convert to the quadratic form. Now, what that's going to look like is trying to consider the most basic version of the exponential that we have. So if we have a look at the screen share rather, of the 3 to the power of 2x stuff, we were able to simplify everything down into just having a basic exponential of 3 to the power of x, and then we substituted a for that thing. In this case, we're able to rewrite everything as a basic form of 2 to the power of x. If you want, you can do a secondary step of making it super clear how this one here can be rewritten. For instance, 2 to the power of x, and then that is squared, using that index law that we have. And now it becomes a lot more obvious that these terms in the middle here are identical. Once we do that, we can do a substitution to make it look a little bit easier. So technically speaking, a substitution isn't required, so long as you can spot that this is a quadratic. It just is a lot nicer to do a substitution, because when you do, you end up with 4a squared is equal to 8a minus 4, and that looks a hell of a lot simpler to solve than this, even though this and that are equivalent. But okay, from here we just have a quadratic. Is there anything to clarify about like why we've done that? Sweet. Okay. Now let's take it from here. So we're just solving a quadratic at this point. How do we solve quadratics? Yep, get it all on one side and make it equal 0. Great start. 4a squared minus 8a plus 4 equals 0. Perfect. Now we've got it all equaling 0. We can do a lot of things here. Name one way to do it, and we'll do that way. Yeah, 4a squared minus 4a minus 4a plus 4. Okay, so you're going to do a sort of grouping thing. 4a squared minus 4a minus 4a plus 4 equals 0. Sure. What else? Yep, there's the grouping. Cool. So you're taking 4a as a common factor out of these two, which is going to get us the a minus 1, and you're taking negative 4 out of these two. So minus 4 bracket a minus 1. Again, a quick validation. Minus 4 into a gets you the minus 4a. Minus 4 into minus 1 gets you the plus 4. And by doing so, you've now got the two a minus 1s there. Nice. It's pretty good. Having those two a minus 1s there is nice, which I'm sure you'll show me why in the next step. Yep, because those are the same term, they are also a factor. A minus 1 comes out, you got 4a minus 4. This is factorized, and it is therefore null factor law. And yeah, I figured what you meant there. All good. So yeah, a equals 1, and... oh, these are the same thing, aren't they? Yeah, these are both a equals 1. Because 4a minus 4, yeah, a equals 1 on both cases. So these end up both actually... no, that's fine. Because you would have had... because you were just writing the equations, right? Yeah. So yeah, both of those will solve down to a equals 1. But we're not quite done yet. We did solve the quadratic, absolutely. But if we think about what we're trying to do, we weren't actually trying to solve for a. We were trying to solve for x. What are we going to do to actually get this into some x terms? If we review where we started, we have x's all the way up until this point, and suddenly we have a's from here. X equals 0, let me think. 1 equals 2 to the x, x equals... yeah, that'll be what it ends up being. How did you end up getting there? Yep, 2 to the power of x equals 1. So you've spotted that if a equals 1, then 1 is now equal to 2 to the power of x. 1 equals 2 to the power of x. And if we think about what index would make that work, well, anything to the power of 0 gets you 1. You could actually do the equating coefficients approach here by rewriting this as 2 to the power of 0 to now do your equating exponents thing from there. But if you already know how to do that, then you wouldn't need to do that because, well, you just see ahead of time that x is going to be 0. So it's kind of a thing that you would never actually do, but it's kind of fun to point out. Yeah, x equals 0. Final answer. In a lot of cases, you get it to a point where you actually have two separate solutions. One of them usually ends up being negative, the other ends up being positive. And in most cases, unless for whatever reason your exponential is a negative exponential, pretty much in every other case you're going to be taking whatever the positive solution is. We saw that in the screen share example, where we had a equals -9 and a equals 3. The -9 was a non-valid solution. Yeah, that's our quadratic solution approach. So we can do more practices on these if we like, or we could move on to the graphing of exponentials. We've hit about halfway. I'd rather you guys have this all locked in before we move on to anything else. Do we feel like we're ready to move on, or do we want to move, or do we want to practice more of these? Oh yeah, also, were there any second chances at looking at the question 2 stuff? Any of this is on the table. Cool. Alright, let's crack on. New content. Graphing the exponential. So here's what the fully transformed version, the general form of the exponential looks like. You're going to have some base of b, and otherwise pretty much everything else more or less tracks with what we're already used to with the exponential, or any other function for that matter. You're still going to have your dilation factors a and d, and your translation factors h and c. The only thing that's a little bit different is, well, 1, there's now a base involved, and 2 is where the horizontal component stuff are located. Because x is in the power, all of the x-related transformations are also attached in that power as well. So the weird thing about exponentials is it's going to be the first graph where, because we now have a new term, the base, that base actually does change how you draw the graph under certain circumstances. You have two main criteria. One is if the base is a number greater than 1, in which case the graph will look something like this, ascending up and to the right in a concave up manner. The other thing that can happen is if your base is between 0 and 1. This is fairly rare, but the textbook does explore it, and so your SAC might explore it too. If your base is between 0 and 1, what we realize is we have what is effectively another way of reflecting across the y-axis. Right, we now have the opposite effect, where we're still ascending up, but we're ascending up and to the left in a concave up way. As for why that is the case, we explored a little bit about the basic graph before, with the base greater than 1, where if you plugged in your values, you got bigger and bigger as x increased. So as x is increasing, the y is getting rapidly bigger, and as x is decreasing, the y's are getting rapidly smaller. When we have a base between 0 and 1, or in other words, just some fraction, well, now you get the opposite effect, where when you raise a fraction to a power, that number gets smaller and smaller, gets closer to 0. So now the positive x's are what's causing it to decrease, and the negative x's, because they are flipping the power, because they're flipping the base to a whole number, are now causing it to increase. So that's why we end up getting the flipped effect. Any questions as to how that works? Because this is if you guys haven't done it yet, this is the first time you'll come across a graph that has this sort of behavior, where it has multiple ways of reflecting. Those are the only real criteria you have to care about. The number here does still matter. Like for instance, if it's 10 to the power of x versus 2 to the power of x, you will see that graph will technically be different, right? Because the base is so much larger than the other one. It's worth exploring it just in case you have to explain your results in like an investigation SAC. But as far as if it just asks you to sketch the graph, you can see that because you set your own axes, these are effectively the same thing. But just for the sake of our learning, a bigger base for this is going to cause the exponential to both rise faster and fall faster. So what we have is there's a bit of a duality there. Because if we look at our base of 2 here, right, how it is increasing and decreasing left and right of the y-axis, you can imagine having a base of 10. You have 10 to the power of 1 is 10, 10 to the power of 2, 100. So you're already getting well and truly faster increases than the other one. On the flip side, 10 to the power of negative 1, 1 over 10, 10 to the power of negative 2, 1 over 100. So we rapidly increase and decrease at a much faster rate based on the base. Same thing here. Essentially, as you get closer and closer to 0, because the denominator gets bigger, when that flips on the negative side, it's going to rise faster, and, well, you get the opposite effect. That only matters if you have to explain it in an investigation SAC. Again, as you're sketching these things, doesn't really drive the decision making so much, unless for whatever reason you have to put two exponentials with different bases on the same axes, which I haven't seen, but maybe your SAC might do it. Dilation factors are a similar story. So rather than changing the base, which as we've seen before will rapidly change how fast or slow an exponential will rise or fall, dilation factor is just a multiplication at the very end. So it's a little bit weaker than changing the base as far as what it does to the shape of the graph. But it also does serve a slightly different effect to it, namely about where it's going to intersect on the y-axis, right? You can see that because we're multiplying a number, rather than them both cutting at the same spot of y equals 1, no matter what the base was, now this one's going to cut at a third, and this one's going to cut at 3. So it does do a little bit different behavior, but again, these graphs are effectively the same shape as far as when you're drawing your own axes. Dilation factors again also exist for the x as well. Here's the differences. The differences again shouldn't matter too much because there's no multiplication on the y value itself. Is why we're getting a similar sort of behavior as before, where they're cutting at similar spots. Next up, reflections. So reflections work the same way as they have in all the other graphs, where the negative sign on the outside is going to flip vertically, and the negative sign on the x is going to flip horizontally. The problem now is that you've now got two different types of graphs that could exist depending on what base you have. So if you have a base bigger than 1 and you're trying to reflect in the x-axis, instead of it going up and to the right, it now goes down and to the right. If the base was between 0 and 1, your original graph would look like this, and so flipping downwards would now look like the blue line. Reflecting in the y-axis is going to be the most annoying one to remember, because the base is itself a way to reflect in the y-axis. So if you have regular base greater than 1, again, the green line, up and to the right, flipping horizontally would cause it to now go that way, which is the same thing as 2 to the power of negative x. But the other thing is, if you started with a base between 0 and 1, you would now have this green line over here, which of course, as you reflect, is going to do the opposite, go back to where we started, essentially. So in other words, what we can kind of see is that these are the same thing, and these are the same thing. And that makes enough sense. The only difference is that the negative is getting distributed into the base rather than staying in the index. We're using that distribution of flipping it as 2 to the power of negative 1, which is just half. So that's like the mathematical reason as to why we're getting very similar results there. That'll be the most confusing bit by far, getting your head around different bases. Everything else is kind of chill. Translations, horizontal translation specifically, again, are pretty much nothing. Horizontal translation, if you have minus, it goes to the right. If you have plus, it goes to the left. Again, doesn't really drive decision making. You'll solve where your intercepts are based off of your algebra. Vertical translations are the more important term, so whatever the plus or minus is at the end will determine where your asymptote is. So if you have a plus 1, you now have a y equals 1 asymptote. If you have a minus 1, you now have a y equals minus 1 asymptote. Just to recap, the reason why we have the asymptote to begin with is because of this behavior here, where as the index, I guess it's over here, huh? Where as the index is getting more and more negative for a basic exponential, you're getting closer and closer to 0. So in other words, the exponential term is tending towards 0. So when you slap a plus 1 on the very end of it, suddenly, as x gets more and more negative, this effectively goes to 0, and what you're left with is plus 1. That's why this is setting the asymptote. Yes, it's a vertical translation, and you can think of it that way, but as far as like a mathematical reason why it does that, it's because this term is approaching 0, whereas this is just a constant. It'll always be 1. But okay. So those are all the fundamental ones. As far as what you need to consider where your horizontal asymptote is going to be, which is always going to be the vertical translation. You just rip that directly from the equation. You're going to need to find your x-intercept, if it exists. Yeah, if it exists. Because as we can see, like this graph here, the blue one, doesn't touch the x-axis at all. So we don't need to find it if we know ahead of time it's not going to be findable. But if we do need to find it, typically what you'll be doing is converting to some sort of logarithm, especially if it's, well, most of them are going to be complicated enough to where you do need to convert to logarithm to solve for the x-intercept. As for the overall procedure, it's the same as any other graph. You set y equals 0 for your x-intercept, and then you just rearrange to get the exponential term on its own directly, and then flip to logarithm. We saw this here. It's just this three-step procedure. Y-intercept you'll pretty much always have to find, because in most cases your domain isn't going to be restricted, and they will always cut at some spot on the Y, in which case you're just going to set your x equal to 0. X equals 0 always gets you Y-intercept. Good news is that's actually kind of chill, because most of the time the exponential just kind of stays as is. Right, you just chuck an x equals 0 in there, and a lot of these other terms can't really combine into each other. Right, a constant is unlikely to combine into an exponential. Same thing with this coefficient here. So it kind of just stays more or less as what it is. Here's the big list of what you need to do. Don't be too intimidated by it. We're essentially just trying to do that thing, and that thing. And half the time you don't even have to do this one. So this is just a catch-all for everything that you need to do. Let's take a look. Okay, so I've given a more complicated one that has a bunch of terms involved in there, just so you can see how they all, just so you can see how the worst case scenario is solved. In any of my guides of graphing, I pretty much always have this step here, which is to rearrange into the general form of the function. This is a good practice to have, because when you rearrange into the general form, you can now clearly see what all of the transformation factors are. So this is not super nice to look at, so one of the first things we might consider doing is expanding it out. Alright, -3 distributed through everything there. -3 and the +1 now, because you've got -3 times -1/3. Now I can see what my vertical translation is. Nice and easy. I don't really need to take this a step further, because I already kind of have everything I need. I don't really care about what this translation term is, but if I did, I'll just take that coefficient of 2 off, so I can clearly see that this would be shifted right by 3. But it's fine to stop here, because for step 2 all we care about is what's that, and this step didn't really do anything to achieve that. So +1 gives us the y equals 1 asymptote. Nice and easy. I throw this step in here because it's nice to know what the overall shape of the graph is going to look like, because we want to know if I should even bother trying to solve for an x-intercept. Because if I know my graph shoots up and right, like that way, it's not touching the x-axis, so why bother? We can just skip that step. So I like to identify if there's any reflection terms in my graph first, because that way I'll be able to figure out the overall shape, and from there determine whether or not I should bother solving for certain intercepts or not. In this case, the only reflection we can see is going to be this negative on the outside of the function, so it's going to be a flip downwards. And because the base is e, that does count as a base greater than 1, so naturally it would have gone up and right, which is why flipping it downwards now brings it down and right. For those who aren't aware or need a reminder, e is roughly 2.7-ish. It's an irrational number, kind of like how pi is an irrational number. So this counts as a base greater than 1. Cool. Okay. Now that we know the rough shape of our graph is as follows, we now know we definitely need our y-intercept and our x-intercept. So let's go ahead and grab those. Y equals 0 for our x-intercept. Rearrange, 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 logarithm. So in this case it's subtracting 1 from both sides, dividing by -3 gets us here. We're trying to get the exponential on its own. And we do our special flip to logarithm, which we'll go into more detail as we look at logarithms. Doing that frees the x in a more rearrangeable way. So we're just going to divide everything by the 2 and then +3 on both sides. And that ends up being our x-intercept. That is the thing that you would write if you have to do it in exact. If they get you to round to a decimal, you're going to be doing calculator anyway, so you don't really care about any of this. You'll just control enter on your CAS and be fine with it. So if you're doing tech-free, that's where you leave it. If you wanted to, you could bring this power into the logarithm, but there's no real need to. It's not considered any simpler. Here's what I was saying about getting your y-intercept by setting x equals 0. You can see it's a very quick and easy thing. Just replace that x with 0 and, well, cool. That's it. That's our number. We got everything we need. We've got the overall shape of the curve. We're just going to label those intercepts with what they should be. that's pretty much it. Any questions or clarifications for any of that? Awesome. If you do have a domain restriction, you handle it the exact same way as all the other functions. Domain restriction, so in this case I'm saying it's between -1 and 3. All I want to do is figure out what are my y values at that spot. So the exponential is a strictly increasing or strictly decreasing graph as is. There's no like turning points or anything that you need to worry about. So when we consider like our domain and range for this kind of function, we're just looking at where does it start and where does it end. There's no funky business going on in the middle that would cause us to worry about did we find the real range or not. So when we're getting our endpoints and sorting that out, we're just subbing in the ends. Alright, so x equals -1, simplify, x equals 3, simplify, and then just label them accordingly. Again, dark circles for inclusive, and open circles, or white circles rather, for exclusive. Inclusive, exclusive. Cool. That's a big lecture on the graphing side of things. Time to put it into practice. So I'll get a screen grab of this summary. I forgot how much Unit 1 and 2 pretty much does nothing with the graphing side of things. You can see these are very simple graphs. Definitely Unit 3, 4, you start looking at least a little bit more complicated, like what we just looked at. These ones, as you can see in question 5, they're not exactly super involved there. But let's give them a shot in any case. What's a decent one? Let's just try A. 5A. F of x is equal to 3 times 2 to the power of x plus 2. Alright, we got a few things we need. We need our intercepts, we need our asymptote, and ideally also the overall shape will help us figure out whether we need to solve for certain intercepts or not. Where are we going to start? What are we going to do? You got a summary sheet as well in the chat if you want to look at the steps involved. Even if you want to just broadly suggest what direction we should head in rather than giving a concrete number, that's fine as well. Okay, well I'll get the easy one out of the way, which is making sure that we have the general form of the exponential. We just want to make sure we're able to clearly see what each of the terms are relating to, and we can, right? It's a fairly simple thing. Got that dilation factor of 3 and that vertical translation factor of 2. That's nice and easy. The next one on our list was to find the asymptote. You don't have to do this in that order, by the way, it's just a nice and natural order. Asymptote, y equals 2. Yeah, absolutely. Whatever the vertical translation term is our asymptote. So if it's positive 2, then our y equals positive 2 is our asymptote. Nice. Next up on our list was figuring out the overall shape of the graph. This is more so just so we're happy and we're seeing what the graph is likely to look like. We're just getting the overall gist of it. So, based on any reflections or any base related information, what shape are we going to have of this graph? I'll see if I can draw all the options here. So we'll call this one option 1, we'll call this one option 2, that can be option 3, and that can be option 4. That'll make it easier to see. Option 1, yeah, option 1 is correct. We have a base that is greater than 1, so it's naturally going to do that. And there's no other reflection terms, so we're not going to have any other things that would cause it to deviate from that natural behavior. So yeah, it's going to behave like option 1 at the location of its asymptote. Nice to know, because now I don't need to give a shit about any of this. None of that x-intercept business needs to matter here. All I care about now is getting that y-intercept. How are we going to get our y-intercept? Is the y in 6? I think it looks like 5, but let me just double check. So for the y-intercept, we're going to let our x equal 0, because that's where it is. Yeah, okay, you got 5 as well. Cool. So it's going to be f of 0, which is 3 to the power of 2 times 0 plus 2. 2 to the power of 0 is always 1. And then now you've just got 3 times 1 for 3, plus 2 for a 5. So you can see my axes is a bit off there. Maybe I would go back and just sort of make that a bit more drastic up. Only a bit though. Yeah. And we're happy now. There was no domain associated, so we assume it's going to be all real. And now that we have the full shape of the graph, the other things were, okay, y-intercept, it said asymptote, and range. So now that we have the shape of the graph, either in our heads or literally drawn on the paper, or in this case the phone, what's the range of this graph going to be? Again, range being all the possible y values they're able to observe. Two to infinity, yep. I'll just correct the use of the square bracket on the 2 there. Because this is an asymptote. Oh, sorry. Yeah, because it's an asymptote, it'll never actually approach, it'll never actually equal 2, it'll just approach 2. So non-inclusive on the 2, and non-inclusive on the infinity as well. So you could say something like y is an element of 2 to infinity. Make enough sense? Okay, because that'll about wrap things up. Are there any further clarifications as to what's going on with any of this stuff? You can see the graphing side of things is on the simpler side as far as the questions they're giving you. It'll be more so the equations side of things. And that's definitely what, just sort of anecdotally, I've noticed that they focus more on in the exam. I can't even remember the last time the graph of an exponential was required in a tech free anyway. Tech active, we don't care about graphing pretty much at all because we just cas it out and it's there. So the graph of an exponential is less important, I'd say, for the SACs. It's more about the solving side of things. But cool. I guess if there's no further questions, I'll leave you guys to enjoy the rest of your day. Thanks so much. Thank you. Thanks.